guys, and welcome back to another lesson in Algebra 1. Today's lesson is going to be about scatter plots. And so this is Unit 5, Lesson 15. And how you know you are successful today is that you can identify if a scatter plot has been positive, negative, or no association. And furthermore, you can make what's called a trend line and use the equation to make predictions. The equations, of course, that we will end up using, we've got slope, slope-intercept form, and point-slope form. And then my sloth is reminding us that there is a thing called the line of best fit, and it may not connect all the dots of the data that is given to us. So we'll see how that comes into play. So let's go ahead and fill out the notes, and I am going to be crazy and try typing them here. So let's see, it says scatter plots, it's used to show data points that show a relationship, hopefully I'm spelling things right, yeah, relationship between two variables, okay, and so two variables, we can also end up calling two variables, you'll hear that called bivariate data. Let me see, I'm going to see if I can do a different color here. Color that makes us happier. Okay. So another name for that is bivariate data. And then bi meaning two and variate referring to variables. So it's like two variable data, which of course linear relationships have x and y. They have two variables in them. All right, let's go to the next one. It says trend line. A trend line you also can hear called the line of best fit. Oh man, it went back to the other color. Let's see if I can try to overrule that here. Okay, so line of best fit, and it can be drawn on a scatter plot that has it is making me pick a color every time. It can be drawn on a scatter plot that has either a positive, let's continue this over here, or a negative association. And so actually, until I get probably smarter at this typing thing, I am probably going to have to just handwrite this because I can go faster handwriting it. So a line is drawn down. Let me go ahead and grab my pencil here. A line is drawn down the middle of the data. And when you draw your line down the middle of the data, you want to make approximately the same number of dots above the line as below the line. This is an and symbol, below the line. And then you are going to write your linear equation in slope-intercept form. Alrighty, so when we are looking at data, particularly real life data does not typically go perfectly in a line. Real life data can have a lot of variance to it. And so, you know, if I'm going too fast, go ahead and pause it. But like this set of data here, you can see you got points that are generally describing a positive association. But they're not necessarily perfectly in a line. And in real life data is like that. Scientific data is like that. Data that is in social sciences is especially like that. So, data won't necessarily have this perfect trend. This is going to be your negative association, and this is going to be no association, where everything's just kind of scattered. So let's go ahead and write down what we're going to write here in these spaces. So a positive association, what we see is both variables increase. So like this situation I gave you here is a distance time one. And so we could use this distance time for anything. I mean, there was no other data given here. It's just kind of some made up data, but it could be like people walking somewhere. Some people might walk faster than others. And so like maybe this person here, they're walking faster, than this person, and that's okay. But, so you get these kind of data points here where distance generally increases as time goes on, because as somebody is walking, they're all going to get further away from where they started as time goes on. And so we get this positive association. You can have a negative association. Oops, I didn't mean to write negative there. Let me go ahead and erase that. Okay, so this is where both variables decrease. And I kind of had this like made up data here, like you've got, time and speed, maybe like, and so this case, like the faster that you go, the shorter amount of time that it takes to get to where you're going, right? So if you were driving a car and somebody is going 70 miles an hour, they're going to take a less amount of time to get there. But if they're going like say 5 or 10 miles an hour, it's going to be much more time to get where they're going. So you can see this, general trend of going down. So both variables are decreasing. All right. Now, no association, there is no relationship. Whoa. Here, erase that. Relationship. So, like in this example, we graph shoe size and number of siblings. Of course, these are not related. Now your shoe size might generally increase, I guess, as your number of siblings go up, in the sense that if you had, say, 5 siblings younger than you, you might have a bigger shoe size than somebody that only has 1 sibling younger than them. If, I don't know, there's really no relationship. So you end up with like this kind of scattered plot here where there's no association. And so this is helpful to know, because if there's no association, there's no way that we can make predictions. And especially when you take math and you apply it to science, in science and in medicine, they're very interested in relationships. If they can figure out, if I do X, then I can get Y to do blank, that is something that is very useful in terms of helping people medically, of developing different scientific implements to, maybe improve like the speed of Wi-Fi, or I don't know, the speed that you can do anything really. So this is, data is very important in that regard. So let's go ahead and look at it in kind of a fun way, which is comparing temperature and ice cream. So we all like ice cream. And as you might imagine, typically what we see is that as the temperature goes up, so when it's 80, you might sell more ice cream. So someplace like Sonic is probably going to sell more ice cream on hot days than it is on cold days, because cold people are like, we don't want to buy cold food. And so you'll see this kind of generally, positive trend. So it says this scatter plot shows the number of ice cream cones sold at a stand when the temperature was a certain number of degrees Fahrenheit. Now notice I kind of broke the graph here because it, you know, the 0 to 50, I don't know, it just make the graph too wide to fit on here. So this little symbol here, it just means that they're like, we removed that chunk because the data that we were wanting to look at was just over here. Okay, so let's go ahead and start, you know, figuring stuff out here. So the first thing that I want to do is I'm going to go ahead and say a let statement. I'm going to say let, you know, let my x equal temperature and my y equal number of ice cream. Okay, so that kind of keeps it straight in my head what I'm going with. And we want to write the equation for the line of best fit. So how we're going to do the line of best fit is we're going to draw a line through here, and I'm going to have to freehand this. Wait, let me see if I can do a shape. Let's see if this will help. So I'm going to have to try to freehand this, which of course means that it's probably going to be not the best. Hopefully, yep, there it goes. Okay, so notice I kind of drew it where, you know, we got about the same number of lines above as we do below. So we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So we got 5 above and 6 below. You can draw this line in slightly varying ways. The best way to do this is to do this with a calculator or a computer, but we're freehanding this, so everybody's going to get slightly different answers in this case. So when we write the equation for the line of best fit, we are going to write this in slope-intercept form. So it's going to be y equals mx plus b. And so what I'm going to do is I'm going to go ahead and first I'm going to find my slope. Okay, and so remember my slope is y2 minus y1 divided by x2 minus x1. So I'm going to go try to figure out a point that is easy for me to estimate. And this data is messy because it is more real life data, but this one looks like right here, this might be like, say, so this part here is 75, so maybe, you know, halfway in between here, we can say this is, say, 73. And then, you know, reading over here, this is 35. So I've got one data point. One data point I can say is 73 degrees. I sell 35 ice cream cones. I'm going to find me another data point where I'm just going to kind of estimate it. So here at 60, I read over here, maybe this is, let's say, we'll say it's like 23. So at 60 and 23, so my rise is going to be, you know, the difference in this and the difference in this. So let's see, we got 2 points, 60 and 23. Remember, we're always writing our x and y in this format. So we write our x first and our y first. So I got my x value here, and I had to kind of interpret where I thought my y value would be. So that's where I'm getting my points. Alrighty, so my y2, we got 23. So we can say 23 minus y1, which is this 35, divided by x1, which is 60, minus 73. Okay, so 23 minus 35 is going to give me 12. And 60 minus 73 is going to give me 13. So then we got a crazy fraction that we cannot reduce at all. It's just 12 over 13. It's almost a 1-to-1 ratio, right? So it's almost 1-to-1. Okay, so we need to just grab a point and we can put it into point slope form. Let me grab a different color. So I'm just going to pick any old point. You know, maybe I'll grab this point here. And so I can do y minus y1 equals mx minus x1. And so my y is 35. Oh, whoops. Let me erase that. We got y minus 35 equals this ridiculous fraction 1213, which is almost 1, x minus 73. You know what I'm going to do with this fraction, this 1213? I'm going to go ahead and just make that 1. I think that's going to make our life a lot easier when we go in and we try to multiply this. I'm just going to make that 1, because it's almost 1. Okay, so we get, let me go ahead, y minus 35 equals x minus 73. I can move this 35 over. And so we end up with an equation, let's see, I'll write it up here. Y equals x minus, so not minus 73 plus 35. We could grab our Desmos because that just makes life a little easier. Let's see, narrow, make this a little narrower. Okay, so we got negative 73 plus 35, and that's going to give me minus 38. So negative 38. This is my equation. It got a lot better when I just made that fraction be 1. Because we're doing this by hand, so it's okay that, you know, I kind of, you know, estimated a little bit with this. So it says, what is the best prediction? And when you go to do this with a calculator in the next lesson, you will get exact numbers because your calculator will tell you this exactly. You won't have to do all of this, but we need to do it the long way before we can do it the short way. So it says, what is the prediction for cones sold when the temperature is 73 degrees? So let me go remind myself. My temperature was X. So when my X is 73, we're saying, what is my Y? I'm going to grab my equation. My Y equals X minus 38. So my Y is going to be 73 minus 38. And so here we go. We got Y equals, let me go grab my calculator again. (73 minus 38 equals 35. Okay, so what this is telling me is that we will sell 35 ice cream cones. And you think about, like, why would anybody do this? This sounds painful. This sounds unfun. But think about businesses that need to predict clothing, like they're going to sell clothing. The problem with if you have a clothing business, like say your Old Navy, you have to decide the year before you sell something what you want to actually buy, and then you have to make predictions. So when when the clothing materializes for summer of 2026, they had to make decisions back in 2025 about what they're going to buy. They had to make mathematical models to say, okay, we know we're going to sell X number of jeans in this particular size, and that's what we'll buy. Because errors in that sort of way either means you have leftovers that you cannot sell, and then it's a loss of money for you, or you didn't buy enough, and so then you didn't have enough to sell, so you didn't make as much money as you could. So math modeling becomes very important when you're talking about businesses that have to make decisions based on what's happening in the future. This also happens with restaurants. They have to make predictions about how much food they have to buy for a Saturday night, because if they buy too much, they have wasted food, and food goes bad, right? You can't use all of it, you know, it goes bad. Okay, anyway, let's look at example 2. So it says, here we got a scatter plot showing the number of hours of sleep. So the number of hours of sleep student got on their screen time in the same day. So we've got hours of screen time and the hours of sleep. Okay. So we want to see what the relationship is. And as you might imagine, this is a negative relationship. So the more time they're spending on, whatever technology, the less hours they're likely sleeping. And so that makes sense that that would be a negative relationship. So it says, write the equation for the line of best fit. So I'm going to go in and I'm going to make my line as best as I can. And I do have an outlier up here. I'm going to kind of just draw the best I can. Not the best. It's kind of terrible, but it's the best I got. Okay, so notice that we do have this interesting outlier here. I somewhat ignored it when I made my line because I went with the general trend of the line. When we do this with the calculator, it'll take those into account. So the line that you draw may be slightly different than the line that I draw because this is freehanding and it's, prone to human error. I could probably draw that a little better. I could probably pick a better one. Let me see. Let's see, it might be something more like that. Oh, that did not go into a... Try this again. Yeah, it's still kind of crazy. Okay, so let's go grab our slope. So first we're going to go grab our slope and we're going to look at, we're going to find our rise over run. Okay, so I'm going to pick a point that's easy. Look, this one, it worked out nice and went through right here. So this point is going to be 1, 9. That made life real easy, thank goodness. This one looks like it went through right here. So I'm going to pick this one. So this worked out much easier than that other one. I didn't draw my line very well in that last one. It made it more painful. Okay, so let's look. This is going to be 7 and it is 6.5. So my rise is how much it goes up. And so it went from 6.5 to 9. So it went from 6.5 to 9. And so when it goes 6.5 to 9, we know that it went up 2.5. And when it went over, it went from 7 to 1. So that's 6. So my slope looks like it's going to be something crazy like 2.5 over 6. And that's the messy nature of real data. It doesn't come out to these real nice, neat numbers. It crossed over in a nice place. Look at this. Crossed over here at 9.5. Okay, so I'm going to make my equation. We got y equals 2.5 over 6x. And it actually crossed here at 9.5. That's where it intersected with the y-axis. That made my life a whole lot easier. So that is my line of best fit. And then it said, predict how many hours a student will get if they have 6.5 hours of screen time. Okay, well, my hours of screen time, that's my x, okay? So my x in this case is going to be 6.5, and I forgot to define my variables up here. We could define that real fast. We could say let x equal screen time and y equals sleep. Okay, so we got x is 6.5 hours and we're looking for y. So we can drop that into our equation. 2.5 divided by 6 times 6.5 plus 9.5. And of course, I have no idea what that is. I'm going to grab my calculator. Okay. So we got to watch this. We got 2.5 divided by 6. I want you to see this is in a fraction and your cursor is in the bottom of your fraction. You're going to have to arrow over, boop, to get out from underneath that fraction bar. So we're going to do times 6.5 and then we're going to add 9.5 and that gives me 36.58333, so 36.58 36.58. And of course, this is, whoa, what did I do here? Oh, I think I did 25 divided by 6. Oh my goodness. So why do I know 36.58 makes no kind of sense? It's because we're talking about hours of sleep. Now, teenagers can sleep a whole lot, right? Like I can sleep a whole lot. I'm not a teenager, but I sure do like sleep. So look, when I did my calculation, I did not put a decimal in for that. I didn't do 2.5, I did 25. So I'm super glad that I did that on camera so you can know and be like, whoa, we don't take numbers just for granted. We evaluate what they are so that we can say, you know what? We did something weird. Oh, and actually, this is a negative slope, so I did even something weirder still. Dink, dink. So I gotta go calculate that again. Okay, so let me erase. Okay, do over. Let's go grab that calculator and let's go put the negative. Okay, now we got 6.79. So now we're getting a more realistic answer. So we found two errors with what I did. I forgot my negative slope, and for some reason I just flat out didn't put my decimal in there. And that's important because when we go to look at these answers, estimating our answer, let's see, 6.79, we need to have an estimate for how realistic it is. In my drawing board, cord just fell out. Okay, so we got y, I already forgot what it was, 6.79, 6.79 hours sleep. That makes more sense, okay? When you are doing your problems, always constantly be checking, is this realistic? Like with my crazy calculation where I ended up with whatever it was, 36 hours or something, like, come on, that was not realistic. And so that was a very good example of how simple errors can cost you points if you are not constantly evaluating your data as you go. Alrighty, until next time, my friends. Bye.